So, good morning. We will continue with the reinforced masonry portions, and today I would like to look at PM interactions for reinforced masonry walls, and then that will lead us to looking at design for bending plus axial load, which is addressed in an empirical manner in the code, in the National Building Code, the section on reinforced masonry. So, before we move into the prescriptions in the code, it is essential to look at PM interactions for reinforced masonry walls, but within the working stress approach. So, what I am going to be doing today is develop the set of expressions that you can use based on the linear elastic behavior, but with the use of the working stresses for both steel and the masonry, and then look at the different zones of the PM interaction curve, so that analytical expressions in those zones can be developed, and you can use that as a design tool. So, depending on the demand in terms of the axial load and moment, if it were to be lying within or on the PM interaction curve, you look at verifying the design or altering the design based on the comparison between demand and the interaction curves itself. However, as I said, the National Building Code prescriptions are empirical in terms of the design approach, and we will examine that subsequently. So, when you are looking at PM interactions for reinforced masonry walls, we are really looking at reinforced grouted concrete hollow block masonry. Now, those could be concrete hollow blocks, or it could be the perforated clay brick blocks with steel reinforcement and grouting. So, we are basically examining either the clay bricks with perforations or concrete blocks, and so the strengths coming from those, the different types of units that you would use is required. And then of course, one important difference in the moment capacities that you would see is depending on the reinforcement configuration in the wall itself. So, the reinforcement configuration as stated here, we are looking at either a spread configuration or a concentrated configuration, right. Now, what do you mean by a spread configuration of reinforcement and a concentrated configuration of reinforcement? If you are using hollow blocks and your wall is made out of 4, 6, 8 depending on the number of hollow blocks that you require to make the entire length of the wall, the placement of the reinforcement, considering that you are designing these as flexural walls, in plane flexural walls or shear walls, the placement of the steel reinforcement can either be concentrated and put at the ends of the walls, which is good in terms of the moment capacity that you will be able to achieve, because with respect to a neutral axis, you are going to be placing a steel reinforcement farthest away from the center of the wall. So, it's a good method to place your flexural steel. Mind you, you are placing your flexural steel farthest away from the center line of the wall itself, and therefore you are concentrating the flexural steel. You could choose to spread the flexural steel, which is okay. Nevertheless, the minimum vertical reinforcement that you require has to be provided over and above this steel that you are providing as flexural steel. So, the minimum spacing requirements between the vertical steel has to be taken into account anyway. Whether I choose to place the steel reinforcement at the ends as flexural steel or not, the minimum spacing of the vertical reinforcement has to be taken into account. So, if you were to place them at the ends concentrated, you might have to provide some additional vertical steel, at least the minimum that the code requires, so that you have satisfied the requirements for vertical and horizontal steel distribution. So, you can either have a configuration where, as you see in the figure, these vertical bars have been placed in all the alternate hollow regions, or you could, and it is spread, or you could ensure that 2 of these bars are placed in the first block and 2 of the bars are placed in the last block, and therefore you are concentrating them. You know that the lever arms are going to be different, and therefore moment capacity will be better in the concentrated situation than the other situation. Of course, it depends on other aspects of how much of area of steel and all that you are going to be considering. So, this is one important difference that is normally checked. The other aspect is you are seeing a situation where in one block, in one of the cavities, one reinforcement bar is placed. Okay. It is most often going to be the case. You will not place a second reinforcement bar inside the same cavity, and this is basically a geometrical requirement. You will not have enough space between bars and clear cover between the, you will not have clear dimension between the cavity and the bar edge itself, which has to be filled with grout. So, from cover considerations and given the size of the cavity, typically it is going to be one bar in a given cavity. So, this is the placement of the reinforcement is up to the structural designer, and therefore, that is one choice you need to make, whether you are going with a concentrated reinforcement or a spread reinforcement. And of course, there is the other requirement, are you going to be looking at a fully grouted wall, or are you going to be looking at a partially grouted wall. So, this again needs to be ensured, and most often what would happen is only the cavities where you place steel reinforcement, it is grouted, and the others are typically left hollow, but then that is again a design choice. So, you really need to know if you are going to be using a fully grouted wall or a partially grouted wall, and make necessary amends as far as your calculations are concerned. So, working stress approach to create the PM interaction curves. So, you need to establish what the allowable stress in your steel is, depending on the steel that you have chosen. Establish Fs, capital Fs, which is your allowable stress in steel. You should know the compressive strength of the masonry, and we discussed this. Of course, you can develop your set of expressions considering the different strengths of the grout and the block itself. However, with the requirement that the grout is at least as strong as the block, and using the strength of the block as the value that you will use for your calculations is acceptable. So, assuming you have an estimate of the compressive strength of the masonry F prime m, you then need to establish what the working stresses are. The working stresses in compression, Fa is the compressive permissible compressive stress, and Fb is the permissible compressive stress, but for flexural compression, where you are allowed to increase the permissible compressive stress by 25%. So, Fb is 1.25 times Fa, and Fb is what you will require. For your stiffness calculations, you will have to use, of course, in this a strength based approach, you are not going to be using the stiffness calculation, I mean you are not going to be using the modulus of elasticity. However, the modulus of elasticity can be estimated as a function of the compressive strength of the masonry that we have seen earlier. So, to make your deflection checks, you will have to use masonry compressive strength, masonry modulus of elasticity. So, those are the parameters that you will require to begin with. Looking at the geometry, I am going to be using this geometry in the ensuing slides, and therefore, it is useful to familiarize ourselves with the notations here. L is the total length of the wall, T is the thickness of the wall, which is nothing but the block thickness in this case, and depending on whether you are going to be using a single block or a double block, then that of course varies. T is the thickness, and then assuming that a spread reinforcement configuration is used and it is symmetrically placed, you have the distances from the edge fiber to the center line of the steel reinforcement, each reinforcement bar of diameter phi, D1, D2, D3, D4 or Di depending on the number of bars that you have. And then all the geometry can be worked out based on these distances from the center line of the bar to the edge of the wall, L, T and the areas of the steel reinforcement. The other thing that can be done is, in this particular case, we are really looking at in-plane capacity. We are looking at in-plane capacity. When you are looking at the out-of-plane capacity, again the choice is how you place the steel reinforcement. Is the steel reinforcement going to be placed for out-of-plane moment capacity in the center of the wall along the thickness, or is there a possibility of having two reinforcement bars placed at the farthest edges within the cavity? So, in the out of plane direction, if you are placing the steel reinforcement at the center line of the wall thickness, you are not going to be able to use the contribution to capacity by the bar, because it is right in the center. Instead, unless you have large eccentricities, instead if you actually place the steel reinforcement apart as 2 bars within the cavity, you can get a better moment capacity in the out of plane direction. So, configuration of the steel reinforcement within the cavities is an important aspect that as a designer is under your control. Okay, so with this configuration in mind, please do keep this configuration in mind. We will start looking at different zones and the expressions that we can use for the calculations of the moment capacity for a given level of axial load itself. So, the PM interaction curves, one choice that you should make in your calculations is whether the contribution of the steel reinforcement to the compression resultant is going to be considered or not, right. So, are you going to be using steel contribution to the moment capacity only after the section cracks is a choice left to you, and in the assignment that you will do with respect to the PM interactions, you will actually check if the contribution by the compression steel is something you must actually bring into your calculations, or is it something negligible. So, assume that we are actually going to be considering the contribution of the compression steel in our calculations that you are going to see in a few minutes, but this is again a choice that you need to make. It is a simple alteration to the PM interaction curve itself. Okay. So, first situation, you have the wall that is subjected to a combination of gravity forces and lateral force, in plane lateral force, and so you have a non-uniform distribution of compression. However, the entire cross section is in compression. So, that is where you begin. Your full cross section is in compression. Your full cross section can be in compression with the condition that there is no bending at all, 0 bending moment on the section, which means the 2 ends, the section is fully in compression, but the 2 ends, the stresses Fm1 and Fm2 are both going to be equal. Now, when both Fm1 and Fm2 are equal, you have a situation where there is no strain gradient, and therefore, you should be using the permissible compressive stress Fa in this case as the limiting compressive stress. However, with any finite value of moment along with the axial force, the limiting stress is no longer Fa, but Fb, which is nothing but 1.25 times Fa that you can consider. So, we are looking at a situation where there is already some bending in the wall, entire section is in compression, all the 4 steel bars are also in compression and contribute to the moment capacity or the axial load capacity. So, C1, C2, C3 and C4 are the resultants of the compressive forces in the bars, whereas the grey area that you see is the compressive stress distribution in the masonry, with Fm1 on one end and Fm2 on the end where the section is less compressed. We are working with an assumption where the entire wall is grouted, and that is again something that you should carefully check between your calculations and actual execution itself. Okay. The first zone is the zone that I have spoken about earlier, and that is pre-cracking. So, there is moment acting on the wall and the entire section is in compression, no tension in the cross section yet. So, in zone 1 no bars are in tension, and therefore, in this situation how do you set up your equations? The value that you see here as Pm is nothing but the resultant of the axial force in the masonry itself. Pm is the resultant of the axial force in masonry. Given that we have some amount of bending now, there is an eccentricity of Pm with respect to the center line in the wall itself. So, that is the eccentricity Em, eccentricity in the masonry due to compression. So, the expressions you now need to be able to estimate, given this distribution of stresses, knowing Fm1 and Fm2. We start with Fm1 and Fm2 values, and we will come to that in a moment. So, you need to be able to make an estimate from the geometry of the distribution of stresses and the geometry of the wall what the resultant forces C1, C2, C3 and C4 are, for which you are basically making use of the triangular distribution of compressive stresses in the wall. The triangular distribution of compressive stresses that you see here, the full wall in compression, Fm1 and Fm2 known, you will be able to use the modular ratio. N here is the modular ratio, N is the modular ratio, that is modulus of elasticity of steel to the ratio of modulus of elasticity of steel to that of the masonry. So, with a modulus of elasticity used, what you are doing in this set of calculations is working on a transform section and arriving at the value of C1, C2, C3 and C4, which are the compression resultants in the bars which are all in compression. So, with respect to the non-uniform distribution of compressive stresses, Fm1 minus Fm2 by the length L into di, which is the distance of the edge fiber from the center line of the bar that you are considering, plus Fm2, which is the section of lesser compression, multiplied by area of steel reinforcement ASI, that is 1 bar by 100 into n minus 1, where n is the transformed area, but you are reducing the area of 1 bar in your estimation. So, n minus 1 is to ensure that you are not counting the bar area twice over. So, you will estimate Ci for each of these situations for a fixed value of Fm1 and Fm2. Let me set up the expressions and then go to the stage wise calculation. The axial force resultant, in the masonry is PM1 Fm1 plus Fm2 into length into thickness divided by 2, that is the axial force resultant from the stress distribution in compression. The moment distribution is nothing but the difference in stresses between the two ends. The flexural compression values are different on two ends, Fm1 and Fm2. So, Fm1 minus Fm2 by 2 into the section modulus gives you the moment corresponding to the this distribution of flexural compression in the wall itself. The eccentricity in this case, that is EMC, that C is jumped out, I am sorry, that is EMC, and EMC is nothing but the moment divided by the axial force. That is how we have been looking at the eccentricity estimates. With this calculated, you have your compression resultants in each bar C1, C2, C3 and C4, and you have the value of the axial force resisted by the axial force distribution, axial force resultant in the masonry itself. So, sigma p is nothing but C1, C2, C3, C4 plus Pm, and similarly the moment summation of the moment sigma Ci, each one into its corresponding eccentricity with respect to the center line of the wall, and the contribution to moment capacity by the masonry portion, which is Pm into the eccentricity EMC. So, this way you have established for each level of stress distribution what the value of axial force and moment capacity is going to be. Of course, in this case, in this calculation, EI is nothing but the distance from the edge fiber to the center line of the bar minus 1/2 of the wall length L by 2. So, these expressions can be used in zone 1, and in zone 1 the expressions that we just talked of are at the bottom, but I am now looking at different stages to estimate the moment capacity. So, my first point is when the wall is in pure compression, my Fm1 is equal to the permissible compressive stress. Since I am looking at capacity, but within the working stress approach, I am starting with Fa as the value of Fm1 and Fa as the value of Fm2. Wall is in complete compression. For this particular case, of course, there is no moment capacity. This is the axial load capacity of the wall itself. So, that is your first stage. Then you start looking at making the compression non-uniform, whereby since a certain moment is also being considered, you cannot use Fa any longer, and therefore, you start using the value of Fb as the limiting stress. So, you use Fb in the second point, I am using Fb, and then keep reducing the value of Fm2 thereby you are considering larger eccentricities, keep continuing till Fm2 becomes 0. Meaning when you say Fm2 becomes 0, that is your limiting condition where the entire wall is still in compression, but any additional moment would mean cracking of the cross section begins. So, the first zone is purely in compression. So, make your calculations using the expressions developed within this range, estimate values of P and corresponding values of moment based on the condition in the wall, stress distribution in the wall Fb, and the reducing values of compressive stress in the lesser compressed edge of the wall itself. So, that is zone 1. Once cracking progresses, you are into zone 2, cracking progresses, and here again you might want to use a tensile strength of the masonry. If you think that the value of tensile strength of the masonry Ft is significant enough, it could be brought into calculations or neglected. You can either neglect the contribution to the moment capacity by the tensile strength of the masonry or introduce that into the calculations, but that is going to be a very small quantity. So, you might as well do away with that additional calculation. So, once the wall starts cracking, you reach a situation where with additional moments, first bar and then the second bar and so on start experiencing tension. So, zone 2 is where part of the section is in compression, the rest of the section is in tension, which means now slowly each bar will start coming into tension, and as the moment on the wall increases, question is what is the tensile stress in the bar and whether the tensile stress in the bar is reaching your permissible tensile stress in steel Fs, and the same calculations will continue, but you are looking at a situation where there is some net section which is going into tension. So, here what I was talking about is, do you want to consider this portion with a certain limit on Ft? You have seen that we can use a permissible tensile stress for the masonry depending on here you are basically looking at tensile strength perpendicular to the bed joint and not parallel to the bed joint. So, you use the permissible tensile stress that is for the direction where tension is perpendicular to the bed joint. It is a small value, you know that the value prescribed by the code is about 0.05 or 0.01. So, the question is whether you want to use that and still make an estimate of the contribution to the moment capacity, the tension carried by the masonry itself. Otherwise, you will have to examine whether the bars are now in compression or the bars have started going into tension. So, I am looking at one of the intermediate situations where at least one bar is in tension, two bars are in tension, and the other bars are in compression. So, this is a check that you will be doing at every stage to see how many bars are in compression, how many bars are in tension. The distribution of the masonry stress is now triangular. So, we are still assuming a linear elastic distribution, and the distribution of from the moment when Fm2 becomes 0, this distribution of stresses is triangular. That change you will have to make as far as the calculations of compression resultant, because the distribution of compressive stresses is triangular now. So, here you basically need to establish whether you are looking at a compressive force resultant or a tensile force resultant at each bar. So, you are making this check, you are checking if the earlier estimate of the compression force in the bar itself, n minus 1 into As I is what we had seen earlier, into Fm2, that is the side which is in tension. So, you are checking with respect to the side in tension Fm2 by alpha L. Now, this alpha L is nothing but the length of the compressed zone, that is it is less than L, alpha is less than 1. So, as the wall starts cracking, the length of the compressed zone is less than the original length L, and therefore, now you are going to be using the value of alpha L instead of L in your calculations for the zone that is in compression. So, we are trying to check if C, the compressive force resultant at each bar, is non-zero or is it positive or negative. Now, if you are getting positive values as far as the notation, as far as the calculations here, positive is considered to be compression, and a negative value of the resultant force would be tension. So, you need to make that check, and if you are looking at a bar still sitting in the compression side, you will continue to use the previous expression, derivation of the previous expression, because now you do not have the full length. Whereas, if the bar is in a zone where tension is present in the masonry, then you will have to look at n instead of n minus 1, now you are looking at n into ASI, because you are not counting the bar diameter twice. So, that change is required, that check is required. Therefore, estimate the value of C1, C2, C3, T, or it might be tension. Once that is estimated, your triangular distribution of stresses is what the compression is in, and therefore, the axial force resultant PM now becomes alpha times L into Fm1 by T, Fm1 by 2 into the thickness of the wall, the triangular distribution of compressive stresses. PM is established, the based on the triangular distribution, again the eccentricity of the compression resultant with respect to the centroid of the triangle itself, L by 2 minus alpha L by 3 centroid, where the compression resultant PM is sitting at the centroid of the triangle itself. And then similarly, the summation of the moments from the bars in compression plus the bars plus the portion of masonry in compression. Similarly, make an estimate of the overall compression resultant C1, C2, C3, C4 plus PM, and you have the estimates within this zone also. Now, you keep continuing in this part of the interaction diagram, you are going to be basically considering lower and lower areas of masonry in compression, right, because you have now reached limiting values of the stresses at the end, the edge compression fiber. Fm1 is Fb, you are already at that maximum, but now with that maximum you are reducing the zone available in the wall cross section in compression. So, you keep reducing the value of alpha and get the distribution of the capacities in the cross section. That is how you would proceed in this particular zone and continue until the first bar reaches a value of Fs into ASI. That means the first bar has well yielded, but not yielded in its true sense, because in the working stress approach it has actually hit the value of permissible tensile force. So, you have reached a stage where one end of the wall cross section is in the maximum value of compressive stress permissible, and the other end, the first bar, has actually reached the permissible stress in tension. That is your balance section. You have your balance section and then continue the calculations with reducing values of alpha. So, you continue reducing alpha until Ti is Fs into ASI, and at this point when the first one reaches Ti Fs into ASI, Ti is equal to Fs into ASI, you reach the balance section. Mark that point as your balance section and continue with the calculations. So, in this segment I have reported the expressions at the bottom, but the different steps, the different points of the PM interaction diagram. As you see, on Fm1 the compressive stress in masonry continues to be the permissible compressive stress due to flexural compression. So, Fb is what you maintain, but what you are actually doing is Fm2 is already 0 as earlier, you have the section has already started cracking, and now the value of alpha is what you are steadily decreasing. You keep reducing the value of alpha, you will see more and more of your bars will go into tension, and therefore, the calculation of C1, C2, C3, C4 and PM, sigma PM and sigma P and sigma M would vary. So, that is your zone 2, you get your balance section also coming within this zone. Zone 3, now the question is, as you keep reducing alpha, you should come to a point where the entire section is now cracked. So, you are basically reducing alpha to values like 0.1 times L, and to do that, once the steel reinforcement bar, as you increase this, as you reduce alpha L, as alpha L reduces, let us assume all the 4 bars have now entered tensile state of tensile stress. Then the tensile stress in the bar will limit the level of compression in the bar itself, in the in the masonry itself. So now you will have to look at what is the level of tension in the first bar, and then corresponding to that would be the compression in the remaining portion of the masonry. So in this, typically you will get all the bars in tension, but whether or not all the bars would actually reach the peak value, the permissible tensile force ASI into Fs, is something that is typically not seen. That is, all your bars may not reach the maximum value of the permissible tension itself. So you keep continuing in this zone, reducing the value of alpha, and now with the steel stresses governing, estimate what is the value of Fm1, the masonry compressive stress. This value will be actually lower than the peak value. This value will be lower than the peak value, and peak value, which is Fb, and you will now see that the moment resistance coming from the compression, the compressed part of the masonry is what is being compromised or lost. Of course, in your calculations you can look at a situation where Fm1 is almost close to 0 and stop there, and at that situation, depending on the geometry of the wall and depending on the location where the bars are, all the bars may or may not reach the value of permissible compressive force Ti here. So that is something which can vary. 3 bars may, in this case 3 bars may reach Fs ASI, whereas 1 bar is less than Fs ASI. So that situation is to be expected. So in this particular case, what you are doing is, with respect to the, since the balance section has been reached, that is, one of your bars has actually reached the permissible tensile stress, you will use the permissible tensile stress in the steel as what is going to govern the behavior of the wall thereafter. Therefore, Fs will dictate what is the corresponding allowable masonry compressive stress. It is no longer going to be Fb, but a value that will be lesser than Fb, but governed by tension, governed by the tension steel. And therefore, in zone 3, the difference is that Fm1 is not predetermined as a value equal to Fb, but Fm1 is estimated based on what the value of Fs is. So again, geometry of the cross section and value of Fs will dictate what value of Fm1 is, and then you will again check whether all your bars are in tension or there are some bars in compression with the same set of expressions that we saw earlier. Estimate C1, C2, C3, C4, or they may become T1, T2, T3 and T4. Estimate again the compression is distributed in a triangular manner, compressive stresses are distributed in a triangular manner. You will still continue to use alpha L Fm1 by T into T, Fm1 by 2 into T as the resultant compression carried by masonry. The from the geometry, the eccentricity in the resultants, and then the moment, total moment, and the total axial force resultants are estimated to complete the section in zone 3. Zone 4 is, so zone 3 you basically have to estimate what is F1 corresponding to the tensile stress Fs, and continuing, this value is now less than the value corresponding to the balance section. That is why alpha is now at a value less than the balance section condition at the balance section. You will then go to a situation where you want to have the 4th zone, which is where you have Fm is equal to 0. So after this zone, the 4th zone is where you will designate that the masonry stress has reached 0, which means you only have the bars in tension. There is no axial force capacity basically in the, there is no compression resultant available. The whole section is in tension. Bars are all possibly at their Fs values, and so you have a moment capacity, but axial force capacity is 0. So then you reach the next critical point of the PM interaction where P is equal to 0, M has reached a certain value. So it's just continuing sections. So now you have no axial load capacity, only moment capacity in the section. Fm1 equal to 0, the resultant in terms of the force, tensile force carried by the bars is nothing but ASI into Fs. So all 4 bars, assume all 4 bars are in their maximum permissible stresses. The compression, that's the tension resultant actually. You will have all the 4 bars contributing to it, and this is 0 because Fm1, so Pm1 goes to 0, Fm1 is 0. There is eccentricity, but now eccentricity is infinity because the whole section is in tension, and so you can estimate what the total moment is, and total this capacity goes to 0 because all this are going to be just tension. Okay. So this is how you would look at 4 zones. Now what we did here was to assume that the compression reinforcement continues to contribute to the moment capacity. We use the reinforcement for both tension capacity and compression capacity, so you could neglect, one way could be to just neglect that contribution, and so just look at where these bars are showing value of Ci greater than 0, which is compression, set that to 0 and look at the PM interaction curve, neglecting the compression reinforcement, and that is a quick check that you can do. So simple checks that you can do is, if you assume there is a finite tensile permissible tensile stress that you want to consider for the masonry, how much does that contribute to the moment capacity? If you were to consider the compression reinforcement, how much is that going to contribute to the moment capacity? How do these PM interaction curves stack up? Okay. So you would get a PM interaction curve of that sort. We are starting off, the reason why it is capped off is because we are starting off with a peak capacity on a peak capacity in compression on one end. So you are capping it off as far as the permissible compressive stress is concerned. So that would be your zone 1 all the way till it cracks. So the upper part of the graph is, this part is zone 1, and then the wall cracks. After the wall cracks, you get into your zone 2 calculations where you are basically reducing the compressed length alpha L, and then you reach the balance section in this state. Once the balance section is reached, and then you continue reducing alpha L, but then once the bars have reached their permissible stresses, you will calculate Fm1 based on what the permissible steel stresses, tensile stresses, and that would be your zone 3, and finally zone 4 is the portion where you are considering 0 masonry, 0 axial force capacity and only moment capacity in the section. So critical points would be only axial force capacity, no moment capacity, then the balance section, and then finally you have only moment capacity, no axial force capacity, and the 4 zones in between. So this is how, of course, you may be familiar doing this for the limit state approach. So one exercise would be to compare this with the limit state approach to create a interaction surface, and then look at the interaction surface that you have created using a working stress approach, and how much more of moment capacity can be considered for the same section but using a different approach. So your next assignment is basically going to deal completely with the PM interactions for reinforced masonry walls. Okay. Before I conclude this section, there is something that I would like to touch upon, and that is the PM interaction behavior for a masonry wall. This particular exercise actually is very instructive from the capacities of reinforced masonry as a structural solution itself. Now Why do I state that as far as the PM interaction curve is concerned? That is because if you look at a masonry wall, okay, if you look at a masonry wall and if you look at the PM interaction curve, we were looking at the axial force capacity at this location, right, looking at the axial force capacity at that location. If I were to introduce more and more steel in the cross section, then basically it is after cracking that you will see increased capacity in the wall. You would see increased capacity in the wall depending on how much steel I am putting in. It is only after the cracking that it is going to contribute. Now, if the level of axial stress in the wall is very high, okay, let us not think in terms of what the code allows as the maximum permissible stress. Let us assume that the compressive stress in the wall is very high, close to the limit that it permits. Assuming that we are somewhere here as far as in that zone as far as the axial stress ratio is concerned, the level of axial stress due to compression divided by the strength of masonry, or in this case the permissible stress in compression. If we are in that zone, steel reinforcement literally has no role, there is no effect in changing the interaction surface for us. But if you take masonry as a structural system, if you look at shear walls and load bearing walls in a masonry structure, we know that the level of compression that exists is typically very low in comparison to the capacity in compression. It is a material which is good in compression, which means most often, even if you are looking at 2-storied, 3-storied structures, the axial stress level in the wall will ensure that you are in the lower portion of the interaction diagram as far as PM is concerned, because you cannot make very heavy, you do not make very tall masonry structures, the level, and because the code also does not allow you to go too far beyond the strength in anywhere close to the strength in compression, the axial stress level will ensure that you are in the lower portion of the axial force moment interaction diagram. Now, why is that good? It is good from two perspectives. First is that it is the region in which the provision of steel reinforcement is going to be beneficial to the moment capacity in the wall or shear resistance in the wall. So, that is the zone where with more and more steel reinforcement that I design, I will be able to get better moment capacities. So, in plane capacities are bound to increase, axial stress ratios are in this zone. That is one thing. The second important thing is, of course, the axial stress ratios are small because we are looking at an entire wall cross section. If it were a column, these axial stress ratios will be high. Would you agree? If the entire structure were not made out of load bearing walls, were made out of columns, the axial stress ratio will typically be higher for a similar plan area. So, it is because of the presence of load bearing walls. Now, if you look at the PM interaction curve and then for different locations on the PM interaction curve, if I were to draw a moment curvature diagram for that section, if I were to make a moment curvature diagram for that section, right, you would get typical moment curvature curves based on section analysis. Now, if for each point on the moment curvature, each point on the PM interaction, if for that section I am estimating the moment curvature, then you will see that the moment curvature, when the axial stress ratios are high or the axial load demand is high, you will have very brittle behavior. The moment curvature will be, the curvatures will be low in those sections. As you come down, the moment curvatures will show better ductility, and when you come to these zones, you will get, when you come to the zones in which the axial stress ratios are low, the moment curvature will show good desirable ductility. So, this situation for moment curvature with very low ductility does not guarantee good ductile performance as far as earthquake resistance is concerned. When axial stress ratios are high, you do not get ductile behavior how much of a steel you want you put in there. So, as a typology, masonry, because of load bearing walls, gives you the possibility of low axial stress ratios. Therefore, you are in a PM interaction zone where moment capacity increases because of the presence of steel significantly, and 2, the moment curvature of the sections there are significantly demonstrate good ductile behavior. So, masonry, reinforced masonry is an excellent choice for seismic solutions as far as providing good ductility, good deformation capacity in earthquakes. This single feature actually makes it a category that is far superior to moment resisting frames. For moment resisting frames, the frame constructions with reinforced concrete columns, the immediate problem that you have is you will not be in the lower portion of the moment interaction diagram, the PM diagram. You will be in the higher portion because of higher axial stress ratios. And because of the higher axial stress ratios, how much of a steel you want you put in there, you will not get ductile behavior in moment curvatures. So, reinforced concrete moment resisting frames cannot give you the desirable ductility beyond a certain limit. Whereas here you have a structural solution that gives you the possibility of achieving good deformation behavior as far as earthquake forces are concerned. So, this is something that you will see is discussed quite extensively in the literature on seismic behavior of reinforced masonry, and I wanted to close the PM interaction discussion with this particular aspect. So, you value the PM interaction that you are doing as a demonstration of good ductile behavior of reinforced masonry itself.